Welcome to our Introduction to Networks IT140. In this presentation, I will provide you with an overview of an important topic that will be part of our course and part of networking in general. So I thought we'll start talking about it as soon as possible to give you a head start and allow you to feel comfortable with this topic of addressing that we'll be using and deploying throughout our course. So the sooner we'll start on addressing, the better. Let's go ahead and take a look at the key points that I'll be covering in this presentation. We'll start first by discussing why addressing, why do we need addressing in the network, and then we'll talk about different types of addressing that we're going to encounter throughout our course, starting with logical addressing, then we'll talk about physical addressing, host names, and then we'll finish the presentation by discussing application numbers. So let's go ahead and start by the need for addressing in the network. So devices in the networks are grouped in local area networks. So what we're seeing right here in this picture, we have grouping of various devices connected to a common point, a switch. This block right here represents a local area network. We have several local area networks displayed in this slide, and we can see that these local area networks are connected together using devices we call routers. So routers are the glue devices that allow us to connect different networks together. A router would have different interfaces. Each interface connect to a different network. And for devices within a local area network, we configure them with the address of that router, which becomes to the device as a gateway, allowing the device to reach other networks. So if a device located on a particular LAN that would like to reach a device on a different LAN, it will send the message first to the default gateway or the router that will process that message and deliver it to the destination on a different network. Now, within the network, we need to have different identifications for devices, just like in the real world. So in the real world, we have names, we have social security numbers, we have house addresses. So we have different forms of identification required to allow for reliable communication in the network. In this presentation, we're going to hit on 4 of the most important type of identifications that devices must be configured with. Logical addressing, which is controlled by the IP protocol. Physical addressing, also known as MAC addressing. Host names, we'll discuss in this presentation the form of fully qualified domain name, or FQDN, and then we'll finish with application numbers, focusing on the topic of sockets and port numbers when it comes to applications. Now I have to mention here that all of these different form of identifications and addressing listed right here will be covered in our course in different chapters in more depth. But as I mentioned in the beginning, it's very important to have some good understanding as soon as possible, because we can't wait till we get to these chapters to be able to use addressing. So you will be using addressing. The sooner you'll learn about them, the more you will be able to grasp what you were working on in the lab and as you read the various chapters. So I hope this will give you an overview and a good introduction to help you out. So let's start with the first form of addressing the devices must have, and that's what we're calling logical addressing. So number 1, logical addressing. Logical addressing, as we said, is controlled by a protocol called the Internet Protocol, or IP. And we have different forms of IP addressing. The most important for us at this point is IPv4, version 4 addressing. Later in the course, we'll introduce a newer form of addressing we call IPv6 that superseded to a certain degree IPv4. But in our network, we're going to be deploying both IPv4 and IPv6 in several labs. So IPv4 is a key part of the addressing that we will be working with. It is logical addressing because this type of addressing, we need it to be independent of the hardware of the network. So we deploy various devices today, from phones to laptops to printers. So all of these different devices, even newer type of devices that we started to see as part of the platform we call Internet of Things, which allows us to use various sensors, even devices at home like refrigerators and microwaves. All of these devices with different hardwares need to be part of the network. So we need a form of addressing that is independent of the underlying hardware of the network. And here comes the IP protocol that provides such address for us. So it's a very important addressing, and it's an address and a protocol that has been around for a long time, that was part of a mandate by the Department of Defense that set out to create a system to connect various devices with different hardware. So that system started a long time ago, and the result of it was eventually the rise of the Internet as we know it today. So IP, the Internet Protocol, started as part of that initiative, and a big part of it is the addressing, the logical addressing we're talking about. So in IPv4, an address that is required for every device that wants to be part of the Internet is expressed in decimal. We write it as a decimal number, like you see right here, 192.168.10.10. So it consists of 4 decimal numbers separated by decimal points. So we use the decimal number system that we are familiar with, that we use on a day-to-day basis. When we type in the IP address in the decimal format that we're familiar with, each number gets translated into memory in machine language as 8 binary bits of ones and zeros. We call an octet. So for example, when I type 192, the first number in my address, that number gets translated to the combination that you see right here of 8 ones and zeros that would give us the representation of 192 in machine language. Same thing for the other parts of our address. So each number is represented as an octet, or 8 bits in memory of the hardware. So the total is 32 bits. So from the beginning, you want to know that an IPv4 address consists of 32 bits represented in 8-bit chunks. We call them octet. Each octet represents one of the 4 numbers that represent the IPv4 address. Now, IPv4 addresses can be assigned statically or dynamically. So you can go in and type in the address on your PC to allow your PC to be part of a network, or you could have your PC request the address dynamically from another machine we call a DHCP server. The process will be discussed later in our course. Same with all the topics we're covering right here. So the first address I want you to focus on is the logical address that is independent of the hardware. Please understand the format of it and how it is represented in memory. So since that address ends up being represented in binary or machine language, it's very important for us to know how to convert a decimal number in binary. That's something that will be important throughout our course in various aspects of the labs we'll be doing. So I'm going to start by a simple conversion example to help you with that process. So if I'm looking at that address we were discussing previously, 192.168.10.10, and I'd like to see how it gets represented in binary, it's a simple process of using a tool. I'm calling that tool the weight template tool. I know that each one of these numbers that I'll use in my address is an 8-bit binary number. So I'm going to use an 8-bit template shown right here. And in each position of this template, I'm showing you the weight of the bit based on its position. So now it's a matter of taking the number that I'm going to translate and simply come up with the combinations of ones and zeros, place them in the right position to give me a total weight, for example, of 192. So let's see what 192 would look like. So I'll start in this position, start on the left of your template, and then place a 1 or 0 in the appropriate position to come up with a weight of 192. So I'm going to put a 1 in the first position right here. Now I have a weight of 128. In the next position, I'll put a 1 as well. So now the total weight of the combination that I placed in my template is 192, which gives me the number that I'm trying to translate. So now for the remaining positions, I don't need to add any weights, so I'll just simply add zeros in these positions. Now if I add the weights of all these 8 bits in my template, I'll end up with the 192 decimal number. So that's what 192 would look like in memory. Let's try it again for the number 168. Again, we'll start with the template, start on the left, and then try to come up with the combination of ones and zeros in the right position that would give you a total weight of 168. A 1 right here would give me 128. A 0 right here is needed because if I put a 1, I'm going to exceed the 168 that I'm translating. So a 0 right here, a 1 right here would take me up to 160. A 0 right here, a 1 right here would give me the 168, so the rest of the bits would be 0. So if I add up the weight again of the combinations, 128 here, 32 right here, that's 160, and 1 right here with an 8, that's 168. So that's the total, that's the combination that will represent 168. Let's do it one final time. This time, let's take the number 255 in decimal and see what combinations of ones and zeros will give us 255. And what we'll find out right here that we need a combination of 8 ones in the template to result in a total of 255. This is a common combination that's going to come up frequently, so keep that in mind. Anytime you look at the number 255 in decimal, it is represented as 8 ones in the memory of the devices. So that is a combination, like I said, that will come up frequently, so keep that in mind. Now, in some cases, certain numbers that we use, certain addressing, like IPv6 addressing, we'll find out that decimal number system is not practical to use. Another number system that will come up frequently in some addresses is the hexadecimal number system. So the hexadecimal number system that we will find out in a number of instances, like in IPv6 addressing as well as in physical addressing, consists of 16 digits. You see them represented in this table right here, starting with the number 0 all the way to 9, and then A, B, C, D, E, and F. The A is equivalent to a decimal of 10, the B 11, and so on. So in this slide, I'm showing you 3 tables, the hexadecimal table that we'll be using in some addressing environment. Next to it is the binary equivalent. We already know how to work with binary from the previous slide, so if you're trying to translate from hexadecimal to decimal, or from decimal to hexadecimal, you'll find out that the binary in the middle right here could be the bridge that allow you to do these translations, since you have that template that we discussed in the previous example. So let's take a look at an example right here. If I'm given the number 2A, notice right here, this is the hexadecimal number. It consists of 2 digits. Now, to distinguish this number from other types of number, we add 0x in front of it. So anytime you see 0x in front of a number, that means what follows is actually a hexadecimal number. So if you're asked to translate this number into decimal, the best way or the easiest way to do it is take each digit and convert it first to binary. So if I take the 2 right here, go to my binary table, here's a 2 in hexadecimal. What combination of binary digits gives me a 2? Notice each hexadecimal digit is converted to 4 binary digits. So I'll simply put the combination for the 2, which is 0010. Starting from the left again, here's a 0, 0, 1, 0. So this combination, which I got from the table right here for the binary, is equivalent to the number 2 in hexadecimal, which is the first number that I'm trying to convert. Then the second number is an A. I go back to the table. What is an A in binary? A in binary is 1010, which is equivalent to 10 in decimal. Let's go ahead and again place the combination of the binary equivalent of A, which is 1010. Now all I have to do is simply add up the weights of all these ones. 32 right here, 8, that's 40, and 2 right here, that's 42, and that's exactly the decimal equivalent for 2A. So 2A in hex is equal to 42 in decimal, and it's equal to this 8-bit combination in binary. Alright, so now we don't want to forget that the first address we're emphasizing with all this talk is that logical address, that IP address. This is a very important address, as we mentioned, is independent of the hardware. Let's go back and visit that address one more time to look at the format of it and the structure of it. So in this slide, I'm showing you an IPv6 address 192.168.10.10. And right off the bat, I want you to understand that a logical address is an address that's made up of different parts. We call it a hierarchical address. So it's not only a logical address independent of the hardware, it is also a hierarchical address, not a flat address. That means it's made up of different parts. And the 2 main parts of that address are the network part and the host part. Think of your house address. Your house address consists of a street address and a house number. So the network part is kind of equivalent to your street name or number. And then your house number is kind of equivalent to the host part of the IP address. So 2 parts, network and host. And those 2 parts must be identified in order to effectively work with the IPv4 address. How do we identify which part of the address is which? That's where we rely on something we call the subnet mask. The subnet mask is a number that is required with every IPv4 address. Without a subnet mask, there's no way for us to tell which part of the address is which. So by definition, the subnet mask, and notice from the name of it, it masks something. It masks all bits in the address that are not a host bits. So any part of the address that's not host will be masked by the subnet mask using binary ones. So let's go ahead and apply this definition. If I'm looking at this address, and if I want to break it into its network and host part, I would use the subnet mask starting from the left, And I'm masking now all the bits in the address that are not host, which means all of these bits on the left of this line, which constitute the network part, must be covered or masked. So I'm going to go ahead and mask them. 192 is a network part, not a host part, so must be covered. You cover it with 8 ones. So here's 8 ones because it's 8 bits. This is what 192 would look like in binary. Since these bits are network bits, they must be covered by the subnet mask with all ones. So I'm using 8 ones to cover these 8 bits. The 168 is also a network part of the address. It must be covered as well. So we mask it with 8 ones. We do the same for the 10 right here. This is a network part of the address. It must also be covered, so we're covering it with all ones. Anything to the right of that line, that's a host part, so we don't cover those bits with ones. We simply use zeros underneath those bits. Now let's take these numbers in our subnet mask and convert them to decimal. A combination of all ones translate, as you remember, to 255. So 255 right here, 255 right here, and 255 right here, representing all those ones above. And for these 8 zeros, the equivalent would be 0 in decimal. So this is what the subnet mask of our address looks like. So whenever we use the address 192.168.10.10, we must include the subnet mask with it so we could tell which part of the address is which. Now there is a simplified version of expressing the subnet mask, and that's called the slash notation. So you could also write the address, same address as 192.168.10.10 followed by /24. The slash notation is another way to express the subnet mask, and what it does right here, it tells us that the first 24-bit of our 32-bit address are the network part of the address. So this is the network part, and the remaining 8 bits are the host part. So you could either use the slash notation for the subnet mask simplified, or you could use the decimal notation which we calculated earlier. So that's your IPv4 address that you need to be familiar with as soon as possible. We're going to start using it, but we'll be talking about it in dedicated chapters in the future. It gives people lots of trouble, so pay attention to it. If you have questions, ask those questions from the beginning of the class so you don't end up getting confused with the IPv4 address. Again, this is a logical address. Know the format of the structure of it. Understand the use of that subnet mask with the address, and understand that the address is made up of 2 different parts. Now, an IPv4 address comes in 3 different types. You have what's called a unicast, broadcast, and multicast. A unicast IP address is an address that is used by a device to reach a single end device. So if this PC is trying to get to this printer, it will send a message to a unicast address representing that printer. A device can also send a message to all other devices on its network using what's called a broadcast address. A broadcast address is used to reach all devices on the local network, on the local street, basically. If I want to send a message to every house on my street, I would use a broadcast address to reach all devices on that network, on that street. Now, very important about the broadcast message does not get transferred to the other networks, because routers that connect networks together by default block those broadcast messages. And the last type of IP address that you need to be familiar with is what we call a multicast, which allows a device to reach only a group of devices on its network. So if you're trying to send a message, let's say, to all printers or all servers. You can group those devices into a multicast group that allow you to send a message to only those devices. Alright, so now we know a little bit about that logical IP address, its structure, its types. The second address that you're going to be running into in this course is a physical address. The physical address is also known as the MAC address, and that's an address that's burned into the hardware of the device. So for example, if you have a PC, you would have a network card in the PC that allows you to connect that PC to the network. The network card, or the NIC, network interface card, that you buy and install on your PC comes with a burned-in MAC address or physical address, as you see right here. So this physical or MAC address is an address that we express not in decimal as we did with the logical IP address, but in hexadecimal. We express it in hexadecimal using 12 hexadecimal digits, as you see right here. So we have 12 hexadecimal digits that are used to express the MAC address that is burned into the NIC card of the device. Now that MAC address, 12 hex digits, remember each hex digit is represented as 4 binary bits in memory, 4 ones and zeros. So 12 times 4, that tells us that the MAC address is a total of 48 bits. Remember, the IP address was a total of IPv4 address was a total of 32 bits. The MAC address is obviously bigger. It's 48 bits, which is represented, we write it down as a hexadecimal number. Now, those 48 bits of the MAC address are broken down into two parts, the upper 24 and the lower 24 bits. The upper 24 bits of the MAC address are referred to as the OUI, or the Organizational Unique Identifier, which is a number assigned to the manufacturer or the vendor that made up this network interface card. So if a company wants to make interface card, let's say Cisco is a major organization that would like to make network interface card, they would get an OUI number from the IEEE organization. The IEEE organization, Institute of Electrical and Electronics Engineer, issues Cisco a number, a unique number that is made up of 24 bits. That number is used by Cisco as the first 24 bits of the MAC addresses for its network interface card. The last 24 bits is simply like a serial number for that NIC that is assigned by Cisco, by the vendor. So every NIC card that Cisco sells will have a 24-bit unique serial number, but all the NIC card of Cisco will start with the same Cisco OUI number issued by the IEEE. The first 24 bits will make up those first 6 hex digits. The last 24 bit will make the remaining 6 hex digits for a total of 12 hexadecimal digits. Here's how you might represent that NIC card MAC address. So these are 6 hex digits right here, 6 hex digits right here. Notice we represent them as two numbers separated by dash or colon in some cases. Again, the first part of the address is the OUI for that company, for Cisco, and the last part of it is a serial number or unique number representing that particular MAC address. Alright, so now every device on the network must be clearly identified. So far we identify the device with a logical address that's independent of the hardware, but you also need a physical address, and that physical address is going to be dependent on the hardware. So we saw a very common form of physical address, which we call the MAC address. But if you're using different hardware, you may end up with a different MAC address or different physical address depending on that hardware. So that's a hardware specific type of address. The most common for us is the MAC address. But in addition to those first two addresses we discussed, every device on the network must also have a name. A host name must be assigned to every device. So names are very important and they are very useful because in real world we like to use names rather than addresses. The physical and the logical addresses we saw previously are difficult for us to memorize and remember. It's much easier for us to know names and remember names. So for example, when we go to do things on the internet, I don't remember or know the IP address of a Cisco server or Amazon server that I'm trying to connect to. I know the name of these devices. So I go to my browser and I enter a name for that device, as we see right here. So for example, this PC is trying to get to another device, a server located in the Cisco network. So you go to your broad browser and you enter the address you're trying to get to or the name of the device you're trying to get to. This name is structured commonly in the format we call a fully qualified domain name. The idea right here is the internet is divided into domains, large domains, like the com domain, the org domain, the gov domain. All of these are domains that make up the internet. So when I'm trying to reach a device, I would enter the fully qualified domain name of that device. For example, this client is trying to reach a device by the name www. www is actually a name of a device. It's a very common name because lots of devices use that name. But that name is unique to each specific network. So this www that we're trying to reach in this example is part of a network called Cisco, which is part of a domain called com. So you enter the fully qualified domain name www.cisco.com to reach this device that you want to talk to on the internet from your PC. Now when you do that, although we like name, prefer name, computers and devices on the internet, routers, switches, prefer physical and logical addresses. So they don't like to use names like we do. They like to use those logical addresses that we discussed and physical addresses. So what happened is that before you can send a message to that server, the Cisco server, www, or the Amazon server you're trying to connect to, your PC sends a query or request to a domain name server. A server on the internet that is available to resolve or translate the name you want to get to an IP address. So a client sends a DNS query, domain name server query, asking that server, hey, I want to go to cisco.com, www.cisco.com. Do you know the IP address of that server I'm trying to reach? If a DNS is available, it will respond back with the IP address of that server we're trying to reach. So our client now has an IP address, and that allows it to complete the message it wants to send to the destination. All that happens in the background, and all that stuff that we'll cover in this presentation, including fully qualified domain name and host name and DNS process, will be covered later in the course. All right. Finally, the last address I want you to be familiar with is something we call a port address. Well, a port address is basically a number we assign to each application that is running on a PC. So if you have a PC, let's say, and you are running multiple applications, we all do that today. So you may have an email program, you may have a web browser, you may have an internet chat, and you may be running them all at the same time. So when your PC send or receive a message, how do we know which one of those applications should handle that message? That is done by assigning what we call port number to each application. So each application is assigned a unique port number that allows us to distinguish the messages that we are receiving and sending and send them to the right application for proper processing. So when a server receives a message from a source device, the first thing it's going to look at is the port number, so it will know which server application needs to process that message. We're going to learn some of these common port numbers later on, and you will learn as well that the combination of a port number plus the IP address of the device, these two numbers together creates a combination we call a socket. So a socket is simply an IP address of a device plus the application port number. That allows us to connect from one socket on one device to another socket on another device. All right, so let's recap right now. We mentioned that we need different forms of identification to have reliable networking today. And the 4 forms of identifications we discussed so far in the presentation are a logical address, which is the IP address. Keep that in mind. The format of it, the structure of it is very important. The sooner you'll know, the better. Then you would need a physical address. That's an address that's burnt into the hardware of the device. You also need a fully qualified domain name that allows you to specifically reach a device by its name. And then finally, you need port numbers for the applications running on those devices. All of that will be covered later. Now I'm going to go ahead and demonstrate quickly some of these addresses on a particular PC. So here on my PC, I'm going to open a command prompt available as part of the Windows operating system, and I'm going to go ahead and investigate what kind of addressing do I have on this PC that I'm using. I have a Windows 10 machine right here, so you could be doing the same thing by opening a command prompt on your machine regardless of what operating system that you might be running. A good command to use to check the IP addressing is the command we call ipconfig. So if you type this ipconfig command on your PC from the command prompt, you're going to get lots of information depending on how many network interface cards you have within your machine. So I have several, that's why I'm getting several pieces of information. But on top, it shows me the information that I have assigned currently to the Ethernet adapter. So that's the network adapter that I have. You can see that I am part of a domain called jccc.name. So that's the local domain for our college right here, followed by the IPv6 address assigned to my machine. And notice it is a large address that we're going to talk about later. We notice right here that we see different digits expressed, and these digits are hexadecimal. So we'll discuss these format of the IPv6 address later on. Following the IPv6 address, you see that my machine does also have an IPv4 address, followed by the very important subnet mask. Without a subnet mask, the IPv4 address is incomplete because we cannot tell which part of the address is which. I don't know the network part from the host part. And then finally, we see that my PC has the address of the default gateway, which is the address of the router that allows me to access remote networks from where I am right here. Alright, so if I want to get more information about my PC, I could type that same command, ipconfig/all. So ipconfig /all gives me more information, more details about the connection. Again, lots of information because I have several cards running right here, but here's my Ethernet adapter now with a bunch of additional information shown. So we see here right before that the name, the host name, that's the name of the PC that I'm using right here, and I'm part again of the domain jccc.name, a local domain, a private domain. And then I see the physical address right here of the interface card that I am using. And notice it is a 12 hexadecimal digits. Notice 12 hexadecimal digit. The first part of it is the organizational unique identifier for the company that created the NIC that I'm using, followed by the serial number for that NIC, followed by the serial number of that NIC. And then you could see the IPv6 address, the IPv4 address, the subnet mask, the default gateway, and notice I have the DHCP server address. Remember that the IPv4 address could be assigned manually or could be requested from a DHCP server. So my PC has requested the address from a DHCP server, which gave me an address. Notice right here, the address has been leased to me, and my lease expires on this date. And on the bottom right here, you will see the DNS server addresses now showed up right here that would allow me to resolve a name that I want to reach to an IP address. If I want to try to reach a device by its name, my PC will contact this DNS server to get help translating the IP address of that device I'm trying to reach to its IP address. And notice there are two of these DNS servers. So lots of useful information that I could get right here with the ipconfig command, and that would be the end of this overview presentation on addressing that I hope would be useful. And the sooner, like I said, you start learning about addressing, the better and the stronger you're going to feel about the rest of our topics in this course. Thanks for listening, and we'll see you in the next presentation.